All right, so now we'll look at the reactive balance control and look at the different motor patterns that we can use, such as the ankle, the hip, the step, and the reach to grasp strategies. Okay, now what we want to know is what motor strategies do we use to respond to threats to balance. And we'll also look at fixed support versus change in support. And then we looked at synergies. So someone that had a stroke, they might have a synergy pattern that might limit our ability to use certain strategies. And synergy is, again, functional coupling of groups of muscles constrained to act together as a unit. And there's actually some really cool computer tomography called posturography that I'm going to show you that we can use to see how a patient reacts and what strategies they use. It's actually very, very cool. And then we can compare it to their normal age group and see how they do as far as balance is concerned. So I'll show you that in a little bit. But let's look at the three strategies. Technically four, but the first one is the ankle strategy. Stand on floor and sway between closely placed objects such as the wall and the table. So you're just kind of using their ankle, going back and forth, back and forth. Okay, you can use a metronome or music to drive slow pacing. Tum, tum, tum. Now their hip strategy is, if you look at, she's really using her hips to maintain good control right here. Okay. And then the forward step strategy from bench is boom. Okay, so she has to use a step strategy. So these are all different ways that you can train balance, reactive balance. Now, reactive balance, you have anterior posterior stability, and how you're going to get that, you're going to use your ankle or you're going to use your hip for forward to back stability. Now, if you look at during the ankle strategy, if you look at during the forward sway, you got your paraspinals working, not so much your abs, but you got your hamstrings working and your gastrocs working. During the backward sway, so as you go backward, your quads are working, your abs are working, and your tibialis anterior is working. Okay? Now, during the hip strategy, during the forward sway, you've got your abs working and you got your quads working. Okay? During the backward sway, during the hip strategy, you got your paraspinals working and your hamstrings working. Okay, so if you look at what's working and what's not working. Now, side to side stability, that was anterior, posterior, forward and back. Now side to side steady, medial, lateral, and multidirectional stability, alignment of body segments and muscles require activation of forces at different joints and in different directions to recover stability. So now, how do older patients compensate for medial lateral stability? Guess what? They add a cane. So if you have a patient that has good forward and backward stability, but they have poor side-to-side stability, give them a cane. Give them a single point cane, and that will provide that. You'll see patients that will walk with a wider base of support. They'll kind of waddle, and that's because they're trying to provide medial lateral stability over anterior posterior stability. So they feel that that's safer when they walk. Now refining and tuning muscle synergies. Postural synergies not fixed. Stereotypical reactions. They are refined and tuned in response to changing demands in the task and environment. So that's what you're doing, is tuning their synergies, and we teach them how to adapt movements in response to task demands. Okay, so sometimes we can't change a lot of things, but we can fine-tune it and teach them how to react. So what you want to understand when you're working with the neurological patient is that we're not going to fix these postural synergies, but we're going to refine and help them fine-tune them in response to the changing demands in the task and the environment. So that's a key component here. So we want to be able to work with a patient. So for example, let's say that a patient we're working on their balance and they're going to anticipate you pushing them. Well, sometimes they may overreact and they may overcompensate, or they may undercompensate. So what we're going to do is we're going to work with them to teach them how to react to someone that's just a slight nudge versus a bigger nudge. And that way they don't overcompensate or undercompensate. So those are things that we want to be aware of. Now, reactive balance control in sitting is a recovery of stability in seated position controls similarly to that in stance. Individual muscles change their reactive activation depending on the direction of instability. Okay, so obviously we want to work on maybe balance control in sitting first, maybe before we do standing, so depending on the individual. Now, clinical application of research, reactive balance responds to unexpected perturbation to stability. And here's the test, which is the Performance-Oriented Mobility Assessment, the POMA. Important not to limit training to activation of a single synergy. So let's, we can take a look at the POMA. And CNS uses anticipatory processes in controlling action, critical to lower extremity activities, and postural activities anticipates voluntary movement. All right, so as we looked at the Denny, which is reactive balance, right? Now we got to look at anticipatory balance, right? We're going to anticipate something. So the CNS uses anticipatory processes in controlling the action, critical to lower extremity activities, and postural activity anticipates voluntary movement. Now, proactive balance in sitting, organization of APAs in sitting varies as function of task demands and environmental characteristics. So clinical applications, ask patients to stand on one leg, ask a patient to lift a heavy object, and some clinical tests. So an example of this would be, okay, so think about, let's say you lifted a box before and you knew a box of dog food. You knew that it weighs 20 pounds, right? So you know that next time you go to lift that box of dog food, you're going to anticipate that it's going to be 20 pounds. So you get ready, your mind says, okay, I remember I got to use these muscles. And then guess what? Someone tricked you and took out the dog food and it was just an empty box, but you still overreact and you put all the money, and what's going to happen is you might fall forward or fall backwards because you were anticipating that dog food to be 20 pounds, but it wasn't. Right? So those are some things that we can adjust to, but someone that has a neurological disorder may not be able to anticipate that, and they may overreact or underreact, and that could be a lot of problems later on. So that's anticipatory balance control. Now, we have sensory inputs for steady state balance. We have vision. That's very important. Position and motion of head with respect to surrounding objects. You need reference for vision for verticality, information for steady state posture. So vision is very important. We need somatosensory contributions. So what do you feel on the bottom of your feet provides the central nervous system with position and motion information about body with reference to supporting surfaces. Reports information about relationship of body segments to one another, role and maintenance of steady state posture. So, right, so you got vision, you got somatosensory, and then you have vestibular contributions. Provides the central nervous system information about position and movement head with respect to gravity and inertial. So these are these sensory inputs, these three inputs of what we need to test all the time. And then I showed you that cool little device that they use, the posturography, that will test all those three different systems. Now, sensory integration, CNS is capable to modify importance of any one sense for postural control. Individuals maintain stability in a variety of different environments. Reweighting critical to maintain steady state balance in changing sensory environments and task conditions. Sensory inputs for reactive balance. Okay, so that was for steady state. Now for reactive works very similarly. We need visual information gathered as the person enters the environment to form a map of the environmental affordances. We need somatosensory inputs controlling body sway when balance caused by rapid displacement of support surfaces. And then we need contribution of the vestibular system in smaller than somatosensory. So vision, somatosensory, and vestibular, all three different systems will work, whether it's static balance, steady state balance, reactive balance, or even anticipatory balance. So clinical applications, again, clinical activities, there's activities to improve organization and muscle activity, activities that promote reliance on alternative senses, right? So if they can't use their vision, we might use their somatosensory. If they can't use somatosensory, you might use vision and vestibular. So understanding that we can go from one to the other is very important. So let me give you an example. So the first one is a sensory condition. Here you're going to use your vestibular, your vision, and somatosensory. You're using on. Look, you can see, you can use your inner ear, and then you can use somatosensory, what you're standing on. So this is pretty good. Then the next thing you can do is give them a blindfold. Now you have to rely on your somatosensory, the bottom, and your vestibular, which is your inner ear. On this one, you put a box around them so that they still can see, but it's dark, and then they have to still use their vestibular and somatosensory. Okay? Since it's dark, you haven't really taken the field of vision out. It's really not accurate to really use vision. So this one, someone could really fall in the dark, like in dimly lit places, movie theaters, parking lots, so you have to be careful. Now your somatosensory, you're using your inner ear, you're using your vision, but now you put them on an uneven surface. So when you put them on an uneven surface, you're putting the somatosensory system, and it's really not accurate. But here, look at this. Now I've taken the eyesight away. I've taken the somatosensory away. So really now we just rely on our inner ear to keep us balanced. The hardest would be putting them on a foam surface, keeping their eyes open, but putting them in a box. And so you've taken out vision, you've taken out somatosensory, now really their inner ear. So you can see where their deficit lies by using this 1, 2, 3, 4, 5, or 6 strategy. It's very cool to do, and it's fun to do in the clinic because patients really like this. And again, if we were in class, we actually have a whole lab where we would have done this. So I apologize, but unfortunately, we're not going to be able to do that. Cognitive systems in postural control, attention resources, information processing requires resources required to complete a task, and then dual task interference, 2 tasks performed simultaneously, attentional resources may decrease in performance on 1 or more tasks. So if you ask a patient to do 2 things at once, they might get compromised from doing the single task that you ask. Then here's the key when it comes to rehab. Don't progress a patient to do something that's more complicated until they mastered a single task. And that's what I was telling you, is that sometimes clinicians get ahead of themselves and try to do things that are too complicated that they might have seen on Instagram or something online, when really each individual needs to be treated on a case-by-case basis. And again, attentional demands vary as function of sensory context. Performance of secondary task not always detrimental effect on postural control, and important to assess balance under both single and dual task conditions. So, have them test the balance while they're just doing one thing, then have them test the balance doing multiple things. So when we look at the brainstem or the brain and say, okay, well, what parts of the brain and the neurological system contribute to steady state balance, reactive balance, and anticipatory balance? So the neural system contributions to postural control are: it's hypothesized that the central nervous system internally represents the body's position in space with reference to behavioral strategies that are effective in controlling movement. So a variety of motor subsystems, including the spinal cord, brainstem, basal ganglia, cerebellum, and higher cortical, contribute to postural control. So, okay, let's break it down a little bit. What does the spinal cord do? Well, the spinal cord gives us ground reaction forces for orientation, present through diminished. The tonically active extensor muscles for anti-gravity support. There's no lateral stability. Somatosensory contributions to postural control. So that's where the spinal cord comes in. What about the brainstem? Well, it controls level of postural tone with combination with the cerebellum. Circuits for automatic postural synergies. Vestibular contributions to postural control. So now you can see, okay, if I have an injury to the spinal cord, if I have an injury to the brainstem, if I have an injury to the basal ganglia or cerebellum, what's going to be affected as far as my posture is controlled. Now, again, if you have an intact system, adaptable postural control system to meet the goals of stability and orientation in any environment, visual contribution to postural control. If you have the basal ganglia and the cerebellum controls of adaptation, abilities to modify postural muscle amplitude in response to changing task and environmental conditions. So cerebellum's pretty important. Basal ganglia has control of postural set, ability to quickly change muscle patterns in response to changing task and environmental conditions. So you can see how if one part of the brain is damaged, they're not going to be able to do certain things. So let me give you an example. This would be a good quiz question. Patient comes in with damage to the basal ganglia. What will they not be able to do as far as postural control? And what might you not do in rehab if that's the case? Well, you see that the basal ganglia controls the postural set, ability to quickly change muscle patterns in response to changing task and environmental conditions. So if you have somebody that has a basal ganglia problem, you're not going to have them quickly change tasks. You're not going to go from one to the other. You're going to take your time and you're going to rehab that way. So understanding where the mechanism or where the injury is, then you can curtail your rehab to that as well. Again, this takes time. It takes a little bit of research versus that cookie cutter recipe that everybody is so used to doing. Again, spinal contributions, orientation component of postural control, tonic activation of extensor muscles for weight support, directionally specific responses to perturbations present at the spinal cord level. So that's where the spinal cord is present. The brainstem regulates regulation of postural tone and automatic postural synergies. The nuclei for processing vestibular inputs to postural control and regulation of anticipatory postural control. So I might say, hey, if somebody has damage to the brainstem, then what's going to be affected? Static, reactive, or anticipatory? Then you can say brainstem anticipatory. They're going to have issues with that. If they have damage to the basal ganglia and cerebellum controls adaptation of postural responses, but the basal ganglia controls the ability to quickly change reactive balance muscle patterns in response to the changing task. All right, good stuff, good stuff.